I was at the Know Thy Star 7 years ago, and that happened to be right after I had earned my PhD, so I talked about my dissertation work there. There will be a quiz, so get out your notes from 7 years ago. And that talk was all about characterizing the photon environment of exoplanets and why that's important. And what I want to tell you today is why that is not enough. We need to do more. And this is the topic of a workshop that happened here on the Caltech campus at the Keck Institute, starting a little over a year ago. So a lot of what you will see is from that. And also, I want to give you a little teaser for some work that's just kicking off so the workshop included everybody on the title slide here. And then those three and I are kicking off an ADS-PS program on coronal mass ejections specifically. We are finding some bare rocks out there. The first, I think, is LHS 3844. The most famous, probably, are TRAPPIST-1b and 1c. And this is a bit surprising. It's not surprising that these planets would have lost their light elements, like hydrogen and helium, but they should be somewhat volcanically active. These are hot planets. They should be developing secondary atmospheres of heavy mean molecular weight species, and those are harder to get off with photons. So a potential solution to this enigma is that these planets have been stripped not by photons, but by corpuscular space weather. So what in the world is a corpuscle? This is the corpuscle. It doesn't have to be a hydrogen atom. Just basically, when I say corpuscle, I mean anything other than light. So that's particles, and it's also the magnetic fields that are associated with the particles. It's also just a fun word to say, so I want to invite you all to say it with me on 3. 1, 2, 3, corpuscle. Yes, thank you. And if I do this right, I will not say particle again throughout this talk. I will say corpuscle. So what about corpuscular space weather? We actually saw an example of this already in Rachel's talk. This is some corpuscular space weather from the sun. This is a coronal mass ejection, corpuscular mass ejections. And they can do lots of things to planets. One of the things that they can do is what I already mentioned. They could be responsible for eroding away atmosphere to produce some of the bare rocks that we are discovering. This is something that's being studied in great detail in the solar system with missions like MAVEN at Mars. They can also mess with the chemistry of the atmosphere. So basically causing reactions that might change your abundances of trace gases, and this might influence life, being able to detect life, basically just interpreting your spectra overall. And that kind of connects back to what Travis was mentioning with that interesting coincidence that I didn't know about maybe when the sun's magnetic configuration changed 400 million years ago, that made it possible for surface life to emerge. I'm very curious about that. This corpuscular space weather is produced by magnetic activity, so it could be that that connection is because the space weather changed on the sun. And then finally, you can induce aurora with corpuscular space weather. And although this doesn't have as many implications for planetary evolution, it's a huge opportunity because this might be our only way to directly measure planetary magnetic fields through the radio emission when the aurora are happening. All right, quiz time. Which of these things also happens as a result of photon radiation hitting the planet? I'll give you a few options and you can raise your hand. In fact, we'll just go through them one by one. Does atmospheric erosion happen? Yeah, totally. Okay, you were paying attention 7 years ago. What about aurora? Kind of iffy. I mean, you could say some analogies maybe with fluorescence there. What about composition changes? Yeah, totally. So all this stuff also happens with photon space weather, but corpuscular space weather does it differently. And sometimes that can have an additive effect. Sometimes it can have a competing effect. Here is an example for the Earth of the ionization rate in Earth's atmosphere, where ionization rate is on the x-axis, not the y, and the y-axis is showing you altitude. I want to draw your attention to the top curve, the orange one. That's due to photons, and you can see that they all get stopped at about 100 kilometers. But if we look at the corpuscles from the sun, those are diving way deeper into the atmosphere. And this level is relevant because that's about where the ozone layer is on the sun. And when these corpuscles hit nitrogen atoms, nitrogen molecules, excuse me, they can split them, produce nitrous oxide catalysts, and those catalysts then destroy ozone catalytically for a long time after the corpuscular event occurred that created them. You can imagine if you took this to the extreme and there was a star that had much more intense corpuscular space weather, you could end up destroying a lot more ozone. And that's exactly what Antigona Segura did in a seminal paper in 2007 that showed basically you could annihilate an ozone layer and it would stay annihilated for years after the event happened. But there weren't really very good constraints on the space weather inputs that she used in that paper. More on that in a bit. If this was a heliophysics or a planetary science crowd, the first 7 minutes of my talk would have been totally in vain because they know that corpuscular space weather is important. In fact, there's this huge fleet of spacecraft out there measuring it right now. So we have made some progress in the last few decades in this area. In particular, Brian Wood pioneered a technique to get some handle on stellar winds. I should back up for a second and tell you about the different kinds of corpuscular space weather really quickly. I showed you what was really a prominence eruption in that video, which was associated with a coronal mass ejection. But there are also stellar winds, which is like a more steady outflow, and then impulsive events, solar energetic particles or stellar energetic particles, stellar energetic corpuscles, I should say. So there's maybe 30 or so of these at the moment. But if we go back to the really dramatic corpuscular mass ejection that I showed you a video of, I'll show you a list of all the widely accepted definitive detections of a coronal mass ejection on stars. Here's your list. Credit goes out to Dave Brain for this joke because he showed it for the definitive detections of exoplanetary magnetic fields, and it's the same list. So the corpuscles are pretty hard to see. And this sets up an interesting problem because we know they're important, but the task of finding them is really hard. And even for the stellar wind measurements, of which there are 30 or so, there's still model dependencies there, and there's still limitations. So there's huge areas for growth to happen there as well. So this sets up a perfect opportunity to have a workshop, basically, and that then led to the Keck Institute workshop that we had here. Evgenia Shkolnik, Joe Lazio, Greg Hallinan, and I put it together, and we brought 30 scientists with very complementary expertise, heliophysics, planetary science, astrophysics, exoplanetary science, all together starting a little over a year ago. We've been working a ton asynchronously since then. All the cool graphics you see in this talk are an outcome of that, and they will be online sometime in the next couple of months. We're still tweaking them, so you can pull them if you want to put them into a talk. They'll be public. And we're working on a final report that would be a good intro to this topic and with ideas for paths forward. That should be out around the end of the summer, I think, if we stay on track. So look for that. And then I mentioned that 4 of us are kicking off an ADSPS program. Oh, getting ahead of myself, apologies. I want to tell you about one of the main takeaways from that effort. It's that there's a ton of potential ways to constrain this stuff. This is a list for stellar winds and coronal mass ejections. I know many of you are probably trying to read down the entire thing right now. You don't need to do that. Just the idea is that there's quite a long list for both of these things. And the limiting factor in progress here really is, like in so many other emerging fields, it's just effort and resources, basically. That's what we need to make progress in this field. So then one thing that the four of us are kicking off right now is this study where we are going to use sun as a star data to get a better handle on one potential metric that I think is really cool for coronal mass ejections called coronal dimming, where the reason I like it is because it's quite straightforward. Basically, you have a coronal mass ejection start, and it starts to literally blow, I screwed it up the whole time, corpuscular mass ejection. It starts to blow corpuscles out of the star, and as that happens, they expand, the emission gets quenched, and you end up with less emission from those corpuscles than you started with. And the amount that declines is related to the mass of the ejection. So look for results there. I'm actually a little ahead of time, but basically, my goal with the talk today was to get this on your minds, more or less. It's something that I think we need to start thinking about as a field. I know it's hard relative to characterizing photon radiation environments. That also is hard, and there's a lot of credit that needs to go to all the work that's been done there. But you can start to think about it. If you do modeling, think about the potential impacts of particles. If you do observations, think about the potential impacts, particularly on transmission spectroscopy. It's not just observing this stuff where we need to make progress. We also need to make progress in the modeling of it and like the laboratory measurements of cross sections and things in order to do the modeling of it. Look for our report coming out near the end of the summer, and go forth and think about corpuscles. I'll take your questions.
As we wait for hands, I'll just remind everybody that we're especially keen on early career folks asking questions after each of these talks, so please feel free to get your hands in the air.
If there are no questions, I'll just talk about one of the other methods that I think is cool.
I was going to ask, so you said that they're camera shy, they're hard to detect.
Yes.
Chair's prerogative this question. So you mentioned that these corpuscles are camera shy and they can be hard to detect. Are there favorite methods or ones that you think are most promising for trying to get one of these bad boys on film?
Yeah, so it depends, of course, on what aspect you're trying to detect. I think the hardest one is energetic particles, probably, at the moment, energetic corpuscles. But stellar winds is maybe, it's the one where we've made the most progress. And I will show you, so I think coronal dimming, and then what Rachel showed, which was evidence of a prominence eruption from Kasuke Namakata, that's great. I think what we really need, and this was one of the other outcomes from the workshop, is the reason there's not widespread agreement on a definitive detection is that these things are ephemeral and you can't go back and validate them. They're kind of in a weird area in that sense where it's sort of similar to exoplanets, I think, like 3 decades ago. We pretty much know they're there. Like it has to be happening, especially for solar analogs. There are reasons it might be different on other stars, and that's why we need to measure it. But they're just hard to see, and especially they're even harder than planets because you can't go back and see them again. It happens and it's over. And so what I think makes the most sense is to do multiple methods, multiple techniques, observing the same star at the same time. And there was lots of agreement at the workshop about this. And Kasuke has actually started that. He had a paper in 2024 where there's some evidence that there is a coronal dimming, that thing that I was telling you about, at the same time as the prominence eruption. So I think those two are a great method. People are trying really hard for type 2 radio bursts, which basically occur when a corpuscular mass ejection produces a shock in front of the material, and you get radio emission from that shock. But so far, no clear detections there. And I'll pause to see if there are questions, but if not, I'll show you one other. Okay, awesome.
One at the back, lovely talk. This is Luke from Carnegie. For the case of Mars, you mentioned MAVEN. What's the current thinking on the relative importance of the particle weather versus other influences?
Yeah, I think it depends a little bit on who you ask, but my understanding is that based on argon isotope measurements, effectively the only way you can explain those is through mass loss mechanisms that require particles, require corpuscles. I don't remember off the top of my head exactly what mechanisms. It might be a combination of them. And you also have to, it gives evidence that there was stronger space weather in the sun's past as well.
Let's do one more quick question up there, and then we'll move on.
Hi Lloyd, great talk. Anish Babraj, UC San Diego. I was curious, do you have an estimate of the kind of corpuscular flux that would be required to destroy the ozone layer for like an Earth-like planet? And if there are any stars which actually have that kind of corpuscular flux?
Let me make sure I understood the question right. Do I have an idea of how strong the particle event has to be to destroy the ozone, and are there stars where that could happen?
Yeah.
Okay. Yeah, well, that is really why we need to measure it, is because what people like to do is to correlate particle events with flare energies on the sun and then extrapolate that to stars. And that's what Antigona Segura did for the 2007 paper I was telling you about. I'm actually questioning myself now. I'm wondering if it's a 2010 paper, but early paper in the aughts. And that was for 80 Leo with a super flare. I think it had an energy something around 10 to the 34 ergs, which is like an order of magnitude stronger than they get on the sun. You have to check my number there. But that one just totally destroyed the ozone layer on that planet. So that gives you an example of what you would need. Okay.
Let's say thank you again to Parke for an excellent talk.